Welcome to Module 21 of the Six Sigma Institute's Lean Six Sigma Certification Curriculum, which follows both the Council for Six Sigma Certification and the International Association for Six Sigma Certification Bodies of Knowledge. A full copy of the Council for Six Sigma Certification's Book of Knowledge can be downloaded from the course description section for free. In this module, we will be discussing the testing of hypothesis in Six Sigma. This module will take approximately 60 minutes to complete. At the end of this module, there will be a 5-question quiz on the topics discussed, which you can complete on your own at any time. You will also find several Six Sigma tools that you can download, including a template with multiple hypothesis tests, an analysis of variance or ANOVA template, and a design of experiments or DOE template, all of which are Excel files. We use hypothesis testing to determine whether your data fits a model, to compare a statistic to an assumption about the population, or to determine whether something changed within the data. In this section, we are going to talk about the basics of hypothesis testing. We will discuss the null versus the alternative hypothesis, as well as the confidence level or risk for hypothesis testing errors. Hypothesis tests are a large part of inferential statistics, where we draw conclusions about the overall process or population by analyzing the sample data and measurements. When stating hypothesis, we are making statements about the population or entire process. While the type of hypothesis test you use depends on the answers you are seeking and the type of data you have, they all follow the same guidelines. You will always begin with a statistic or criteria that you usually compute from your sample data. From there, you will create a null hypothesis and an alternative hypothesis, but the null or alternative needs to keep in line with the type of test that you are dealing with. Like the chi-squared goodness of fit test, the null hypothesis is that the data was normal, and the alternative hypothesis is that the data was not normal. Then the statistic or criteria is compared against the reference criteria or distribution. How the calculated statistic compares to the reference criteria determines whether you accept the null hypothesis or reject the null hypothesis in favor of the alternative hypothesis. Hypothesis tests have two main parts, the null and the alternative. The null hypothesis is abbreviated as HO and is usually a statement about the data that reflects no effect or no difference. The alternative hypothesis is abbreviated as HA and is usually a statement that is likely to be true if the null hypothesis is not true. In short, if we reject the null hypothesis, we accept the alternative hypothesis. Typically, the null hypothesis is an equal statement of some type. The mean of the new process is equal to the mean of the old process. The distribution of the data is equal to the normal curve. The alternative hypothesis is typically written as a not equals, a greater than, or less than statement. The mean of the new process is greater than the mean of the old process. The distribution of data is not equal to the normal curve. How you write the alternative hypothesis depends on the question you are asking and the type of hypothesis test you are running. Anytime you draw inferences about a population from sample data, there is at least some likelihood of error. With hypothesis testing, errors come in two types. In a type 1 error, the null hypothesis is rejected when it is actually true. This is also known as the producer risk, and the probability of risk is measured by alpha, where the alpha risk is a probability between 0 and 1, a percentage between 0 and 100. In a type 2 error, the null hypothesis is accepted when it's actually false. This is also called the consumer risk, and the probability of the risk is measured by beta, where the beta risk is a probability between 0 and 1. To describe the risk, and set up our hypothesis test for what we deem to be an acceptable risk, a confidence level must be picked. The most common confidence level used is 95%, or an alpha risk of 5% in decimal form. Typically, the confidence level is set with the type 1 error in mind, so you use alpha for the confidence level. The beta value is associated with the sample size and power of that sample. In order to determine which test to run, you must know what type of data you have, the number of levels of interest, whether the data has a normal distribution, and what you are testing. In this section, we are going to discuss the hypothesis selection process. We will discuss the differences between the 1 and 2 proportion test for discrete data, the differences between the 1 and 2 sample t and chi-squared tests for continuous normal data, as well as the differences between the chi-squared, 1 sample Wilcoxon and Mann-Whitney tests for continuous non-normal data. As we have discussed previously, discrete data are counts and continuous data are measurements. While we prefer working with continuous data in statistical analysis, we still have options when it comes to working with discrete data. There are two separate tests to choose from, depending on how many factors of x and how many levels of interest for x we are seeking. Regardless of the test we choose, both are used for comparing proportions between the sample and the target. We use the one proportion test when there is only one factor for x and only one level of interest for x, the input. We typically have only one set of data, which is the sample and the target. The one proportion test is used solely for comparing proportions, such as percentage or rates, between samples and a target. The null hypothesis is that the sample is equal to the target, whereas the alternative is that the sample is not equal to the target. We use the two proportion test when there is only one factor for x, but there is either one or two levels of interest for x. We typically have two sets of data, and you are comparing those data sets. The two proportion test is used solely for comparing proportions such as percentage or rates between sample and target. The null hypothesis is that the proportion 1 is equal to proportion 2, whereas the alternative is that proportion 1 is not equal to proportion 2. Continuous data is data that can be measured. It consists of measured values that can be anywhere between an infinite array of whole numbers. When dealing with continuous data, we have different tests to choose from depending on whether the data is normal or not. In dealing with continuous normal data, the hypothesis test that we have in our tool belt can compare the sample with the standard deviation, variables, and even references. We can also compare two samples against one another. We use the one sample or paired t-test when we are comparing means. Typically, the t-test is used when working with smaller samples, and the z-test is used when the samples are larger. If we want to compare the sample of the mean against a target, then we will use the one sample t-test. But if we want to compare the mean of a sample against the mean of another sample for the same factor of x, then we would use the paired t-test. Generally speaking, when using the paired t-test, the first sample is the baseline and the second is taken after the change is made. We use the test to see if a change made a difference. The null hypothesis is that the mean of sample 1 is equal to the mean of sample 2, whereas the alternative is that the mean of sample 1 is not equal to the mean of sample 2. We use the chi-square or one variance test when we are comparing the standard deviation or variance between samples. If we are comparing the standard deviation between two samples for the same factor of x, one taken before a change to the process has been made and one taken after, then we can use the chi-squared test. But if we are comparing the variation between two samples of the same factor of x, then we will use the one variance test. The null hypothesis is that the standard deviation or variance of sample 1 is equal to the standard deviation or variance of sample 2, and the alternative hypothesis is that they are not equal to one another. We use the two-sample t-test when we are comparing the means between two samples of data for different factors of x. The two-sample t-test might seem like the one-sample t-test because in the one-sample t-test we discussed how you might compare a sample from before a change to a sample after a change. However, the two-sample t-test is slightly different because you are comparing two samples from different populations. The null hypothesis is that the mean of sample 1 is equal to the mean of sample 2, and the alternative hypothesis is that the mean of sample 1 is not equal to the mean of sample 2. Lastly, we have the hypothesis test for when we are working with continuous data that is not normal. This includes the chi-squared test, the Mann-Whitney test, and the one-sample Wilcoxon test. These tests are used when the data is not normal, and it allows us to compare the sample with the standard deviation, variables, or even references. It can also be used to compare the medians between samples. If you haven't already noticed, the chi-square test is used fairly often in Six Sigma. We can use it to determine our data is normal or non-normal, so therefore we can use it anytime we are working with continuous data, regardless of whether it is normal or not. We use the chi-squared or one variance test when we are comparing the standard deviation or variance between samples. If we are comparing the standard deviation between two samples of the same factor of x, one taken before a change to the process has been made and one taken after, then we can use the chi-squared test. But if we are comparing the variation between two samples of the same factor of x, then we will use the one variance test. The null hypothesis is that the standard deviation or variance of sample 1 is equal to the standard deviation or variance of sample 2, and the alternative hypothesis is that they are not equal to one another. We use the one sample Wilcoxon when we are comparing the medians, not the mean, between a sample and a hypothesized sample, or even when comparing a new sample to a sample taken before a change was made. It is typically used when data is somewhat symmetrical. The null hypothesis is that the median of one sample is equal to the median of the test sample, and the alternative is that the median of one sample is not equal to the median of the test sample. Like the one sample Wilcoxon test, we use the Mann-Whitney test when we are comparing medians. But in this test, we are comparing the medians between samples of two factors of x rather than one. The null hypothesis is that the median of one sample is equal to the median of the second sample, and the alternative hypothesis is that the median of one sample is not equal to the median of the second sample. At this point, a common question about hypothesis tests comes up. Why go through the trouble to run statistical tests to determine if things are different? When introducing the normal curve previously, we noted that it is not always enough to see that a histogram appears to be symmetrical and following the normal curve. Raw data can be deceptive, which is why we ran the chi-squared goodness of fit test in Excel to ensure that the data was normal. The same principle is true when comparing statistics from samples. Yes, one sample can have higher values, but is it statistically different? Six Sigma teams cannot just answer the question, is the number different? They must answer the question, is this number so statistically different that we can take action on this information? Statistically different doesn't have to do with scale. In one process, the difference between 10 and 23 might not be statistically different. However, in another process, the difference between 10 and 10.5 might be statistically different. Regardless of the test that you are running, hypothesis testing generally follows the same series of steps from start to finish. In this section, we are going to discuss the steps of running a hypothesis test from beginning to end. In the Council for Six Sigma certification book, which can be downloaded from the course description section, there are 7 steps listed, but for ease, we have combined several of them here, so we will cover the 5 fundamental steps. We will also talk about using the hypothesis test in multiple phases of the DMAC methodology, as well as review some of the most commonly used terms. We start by stating the null and alternative hypothesis. The null hypothesis is always written from the perspective that no change or difference occurred. The alternative hypothesis is always written from the perspective that a change or difference is present, either not equal, greater, or less than. Remember, the null is always represented by H0, whereas the alternative is represented by HA. Next, we set the confidence level for alpha. Usually, the confidence level is set at 95% for alpha, but other common settings are 99 and 99.9%. A confidence level of 95% means an alpha value of 0.05 or 5%. A confidence level of 99% means an alpha value of 0.01 or 1%. And of course, a confidence level of 99.9% means an alpha value of 0.001 or 0.1%. Setting the confidence level too high can prevent testing errors from occurring, but can also prevent you from making a decision based on the test. Then you need to decide which hypothesis test you are going to use. Are you working with continuous or discrete data? If you are working with continuous data, is that data normal or not? What statistic are you working with? Is it the mean, variation, or the median? How many sets of data do you have to work with? How many levels of interest in X are there? Remember that when you are working with more than 2 sets of data, you might want to use the design of experiments or analysis of variance. Be careful in your selection because choosing the wrong test can provide inaccurate or unreliable results. Next, you need to select the most appropriate sample size. You need to ask yourself what the cost of a type 1 error is and decide whether setting an alpha risk level to 5% is enough. You also need to ask yourself what the cost of a type 2 error is and whether setting a beta risk level of 10% is enough. You will have to choose a delta level as well. We have not discussed sample size in detail yet, but we will cover it soon enough. While there are a few manual calculations that can be used, it is important to remember that an incorrect manual calculation can skew the results of any test. Finally, we need to run the test and then analyze the p-value. Remember when we discussed the chi-squared goodness of fit test for determining whether our data was normal or not? We had to set our alpha risk, and we generally set it at 5% or 0.05. So when we run any hypothesis test, we will be provided a summary of the results, and in that summary, we will be presented with the p-value. We then compare the p-value against the alpha risk. If the p-value is greater than the alpha risk, then we accept the null hypothesis, which is that the samples being compared are equal to one another. But if the p-value is less than the alpha risk value, we reject the null and accept the alternative hypothesis, that there is a difference between the 2 samples being compared, that there was a change in the process from before and after a change was implemented. We generally run the chi-squared goodness of fit test in order to determine if our data is normal or not in the measurement and analyze phase. But virtually all hypothesis tests will be conducted during the last 3 phases of the DMAC methodology. In the analyze phase, we use hypothesis testing to determine if an input can be the root cause of the problem we are seeking to correct. In the improve phase, we use hypothesis testing to validate solutions that we are testing. And in the control phase, we use the hypothesis testing to monitor the solution and ensure that it stays within statistical control. Now, just as a quick review, since we introduced many new terms, the null hypothesis is the assumed hypothesis. It is a statement that nothing has changed or no statistical difference exists. The alternative hypothesis is a statement that something has changed or is statistically different. It can be framed out as a not equal, greater than, or less than. The alpha value is the measurement of risk of a type 1 error. The null hypothesis is rejected when it is actually true. The beta value is the risk of a type 2 error. The null hypothesis is not rejected when it is actually false. A test statistic is a standard value that is used to calculate the p-value in order to determine whether to reject the null. For example, in the t-test, the value is t. We didn't calculate or discuss these values in detail, but they are shown in our output summary for the test. These statistics can be valuable for more advanced statistical calculations. The p-value is the number typically used to compare the alpha value in order to determine whether or not to reject the null hypothesis. The null hypothesis is rejected if the p-value is less than the alpha value.